Good afternoon, ladies and gentlemen. Welcome to Sound Learning session about measurements, the measure of mankind. Today's presenter is Ken Selger, as I like to call him, our walking encyclopedia. We are going to be starting our session very shortly. I just wanted to go over a few housekeeping rules. At this point, all of you are going to be muted. We're going to wait for the section for questions at the end of the session. And once you're ready to do so, go ahead and raise your hand. One of the options at the bottom of your screen is raised hand, or you can type in a question in Q&As. And we will be responding to your questions. Once the question is asked and a hand is raised, I will then unmute yourself, and you will be able to ask a question in real time. And without further ado, I am going to unmute Mr. Selger, and he's going to take us to the world of measurements.
Welcome to Sound Learning session on measurements. This will be a relatively brief session, but I hopefully be full of lots of information that you can use as you go through life. So what are we going to cover today? Well, we're going to start off with the history of measurements, why measurements are important, measurements in the United States versus the rest of the world, our measurement standards and the problems that they are having, and the solutions that we have come up with, and how this solution has opened up the secrets of other things in this world. And light waves turn out to be our most sensitive measuring stick. So, who am I? Well, I have a degree in physics, and I've taken a number of classes up at FGCU. I've been a principal engineer with PerkinElmer. I had my own small business with computers. I worked on the Hubble. I have a system up on the International Space Station right now. And I was an optical engineer with the Hexagon and Corona programs. So going into what I did, I am what I consider an engineering physicist. My first job out of college was in measurement standards. I was in the measurement standards lab, and we were building the Atlas and Centaur missiles. We certified the instruments used to make those missiles to in some cases to a millionth of an inch. And you can see the Atlas on the right, and down in the lower portion of the picture is a photograph or a drawing of some optical flats which are being measured, and they are literally down to a millionth of an inch. So measurements has a long history. God said to Noah, build an ark, 300 cubics by 80 cubics by 20 cubics. Noah says, what's a cubic? So, people have been using measurements around for many, many, many years. So what we're going to expect to see today is we'll start with the measurements we commonly use, and I'll show you why there are problems with the measurement standards behind those measurements. Next, we'll look at the new measurement standards, and we'll cover some of the practical things you may not know about them. And at times we may seem to go a little off topic, but we'll come back to our measurements as soon as we can. So, what are the everyday measurements? They're yards, millimeters, pounds, kilograms, all the other usual things that you usually see. And they are the fundamental measurements of length, mass, and time, or a combination of them, like miles per hour. And the miles per hour is a speed measurement, and they have different kinds of standards or usage depending upon the application. At sea, it's knots. And on the highway, it's miles per hour. But for an astronomer, it's light years. So they're all different depending upon your usage. And it's important to understand that sometimes the measurements may not seem what they seem like they are. Here we have a picture of a 20-pound grill tank commonly used on most home grills and also on these fire pits that we have here. So what a lot of people do is when they run out, they grab their tank and they run up to a local store and get a Blue Rhino swap out tank. And it's great, it's convenient, but most people don't realize those tanks only have 15 pounds of propane in them. They cut them short. So you're paying almost the same amount for a full 20 pounds if you could get to a filling station, which could fill your tank. I generally do, but I have 2 tanks, and I always keep one full in the garage, ready to go when my primary tank is empty, and I drag it off to a filling station. And there are 2 of them nearby, relatively nearby. One's up at Alico, and the other one's down on Bonita Beach Road. I go to the one on Bonita Beach Road, it's Thompson's Propane, and they do an excellent job of inspecting the tank. Many people don't realize tanks have a life expectancy. The Department of Transportation has ruled that they must be replaced or recertified at the end of 12 years. And Thompson's can do that. They inspect the tank and they do a thorough job of making sure there are no leaks and that everything is in good condition, has the proper valve. The valve has been replaced by a new standard that they're using, and they fill up the tank. And off I go after about 2 or 3 minutes of waiting. So it's a good way to do it, but certainly I can't complain, can see why people would love the convenience that they get by being able to go off campus and get a new tank very quickly. So the measurement systems out there, what was originally around was the imperial system, where the king settled all the measurement disputes. It was his foot, his arm, that were the standards. Noah's cubic, for example, was an Egyptian measurement of the pharaoh's forearm. So the metric system came along, and the first question I'm going to ask you is, who invented the metric system? So most people don't realize it was invented by the French. And when did they invent it? Well, it was back in the French Revolution of 1789. And why did they invent it? They were trying to they were trying to purge everything that had a royal connotation to it. So they wanted something that had good repeatability, reproducibility, and was completely independent of country or royalty. So the advantages of the metric system is that everything is based on a power of 10. So 10 millimeters is 1 centimeter and so on. In international trade, everyone uses the same system. So who uses the metric system? Well, all the countries in gray use the metric system. And you'll notice that there is this one big outfit in the middle of your picture called the USA, which uses what they call customary system. And there's 2 other little tiny countries that also use their system and don't use metric. But as I said in the previous slide, when it comes to international trade, everyone does use metric. So what's the cost to us of a non-metric standard that we use? One estimate is that there was a $6 billion a year cost, but that does not include jobs lost because we not metric, and so people don't even offer us a job that would require metric work. Jobs not bid because it's metric, or the expense of having 2 measurement systems, both a customary and a metric. It generates manufacturing errors, and you need to be trained in 2 different systems. So those are the parts that go into that $6 billion a year. NASA lost the Mars probe back in October of 99, and it's believed that it was due to a metric conversion error. Cost $125 million. So who's responsible for our standards? Well, the US Constitution in Article 1, Section 8, Congress is to fix the standards of weights and measures. So it's been around since our founding fathers. They realized it was important to make sure that we had a good set of standards. And they created a outfit or a agency called the National Bureau of Standards, which morphed into the National Institute of Standards and Technology in 1995. And they added some additional capabilities or skills into that particular agency, in particular in nanoscale sciences, information technology, neutron research, material measurements, and physical measurements. So how did the French define the meter? The meter was defined as the distance between the North Pole to the equator, going through Paris, of course, and it was 1/10,000,000th of that distance. Now, it's something not too easy to go check every day. So using that definition for the meter, weight was defined, and weight was defined by a cube of water, 10 centimeters on a side, at the melting point of ice. So you can see where the definition for length plays into this particular item as well for weight. And it's also a liter. So time, however, the French did not bother to change in any way. It's still a 24-hour solar day, 60 minutes in an hour, and 60 seconds in a minute. And we're going to go into this one a little bit more depth as we go along. The temperature, again, the United States is the only country, and I mean the only country, which uses Fahrenheit. And it was based on some faulty science. It was based on what they thought was the freezing point of seawater. They thought was 0 degrees. And they thought that the body temperature was 100 degrees. So those were the 2 points to make up the scale. And then everything was sort of scaled from that. So the centigrade scale is simply the freezing and boiling points of water. Kelvin is another scale. It's the same scale as the centigrade scale. However, it's biased by minus 273 degrees. So at 0 degrees, Kelvin is minus 273 centigrade. And it's used in the scientific world. And it's based on where all motion, all molecular motion stops. And it's calculated based on how much motion shrinks as you move down in temperature. You can't quite get there. They've gotten very, very close to absolute zero, a fraction of a degree, but they never can quite get there. So how were the measurement standards kept? The French kept a meter bar, and they decided after some trial and error to keep a meter bar made out of platinum. And it was chosen because it was very, very stable. So it was not have any changes with time. But it was not easy to reproduce the meter. It was a pair of scribe lines on this bar with a pair of microscopes that were focused down on the scribe lines to represent, to see exactly where those lines were. So time, though, there's 2 different times that people are concerned with. Most of us are just use the solar day, but unfortunately, the solar day is not constant. So the solar day is when when the Earth looks directly at the sun, and it varies from day to day and throughout the year and from year to year. So there's a secondary day, sidereal day, which is when the Earth rotates 360 degrees. So this graph will show you what I mean by that. You can see in position 1, the Earth looks directly at the sun. After rotating 360 degrees, it has also moved along its elliptical path around the sun and looks past the sun. It takes it a little further along the path before it rotates enough to look directly back at the sun. There's about a 4-minute in time difference between the two positions. So the Earth is actually slowing down in its rotation, has been slowing down for billions of years. So why does the Earth slow down? So the Earth has tides, these water that's around the Earth, which cover 70% of the Earth, actually slow the rotation down. And the tides are controlled mostly by the moon. And the moon itself also has tides, has no water, but there are land tides. And the moon is somewhat asymmetric in its distribution of weight. And what has happened over billions of years, the moon has stopped rotating. And the weighted side of the moon looks at the Earth and just stays there. That's why we only see one side of the moon. It doesn't rotate with respect to us. And eventually, the Earth will slow down and stop, and we will both be frozen or locked, and the day will be infinitely long. Now you can get everything done in a day. So, how do we get around some of these problems? Well, the standards must be constant and reproducible. So the meter has been redefined as the distance light travels in this fraction of a second. And the reason it goes that way is because of Mr. Einstein, Dr. Einstein. Light travels at a constant speed, regardless of where it is or how it is. It's a constant. So now we had something that we could use that was not varying with time or place or anything else. And so that's how distance was defined. To get the time correct, they took a element, cesium, the 133 isotope, which blinks on and off at 9 billion times a second. And that was the definition of a second. So now we had the time and the distance was all controlled by the speed of light. And it was also the invention of the atomic clock. The atomic clock is the cesium-133. So how does this work? Back in the 1950s, the National Bureau of Standards came up with the first cesium atomic clock. And it had a uncertainty in its time in the order of 10,000 nanoseconds per day. Now, a nanosecond is a billionth of a second, so it's not a very big number. But as they went on in time, and they went into the 60s, 70s, and 80s, they kept making newer clocks, which got better and better and better. And now we have uncertainties in the order of a tenth or a hundredth of a nanosecond per day. Essentially, we know exactly what the time is anywhere. So now with the time known to such precision, That allowed us to produce a thing called GPS, Global Positioning Satellites. So the satellite, how this works is the satellite transit time is measured through an atomic clock. And that transit time defines a ring on the surface of the Earth where that transit time is the number that you come up with. By using 3 satellites and 3 rings, which overlap, their intersection is where your location is. So when you have 2 of them, there could be 2 places where you could be located. But it turns out when you have 3, there's only one unique place where all 3 overlap, and that's where your position is. So that gave us GPS. The next thing that we are going to talk about briefly is measuring distance by light. And most of us, or many of us around here, use a laser rangefinder. And the laser rangefinder uses the speed of light and the transit time to measure the distance to the flagpole reflectors. You can see some flagpole reflectors in the lower left that are typical of what we have here at Pelican Sound. There's a diagram in the middle showing how they bounce the light around and send it right back to where it came from. And astronomers have used the same principle to determine the distance to the moon, which was really unknown to a fairly large number until the astronauts got there and put a bunch of these retroreflectors, which is what they're called, on the moon. And there's a picture of the retroreflector that was dropped off by Armstrong and his crew. And it's still today, working today. They can bounce a laser beam off of it and measure exactly how far away the moon is. Now, this is a little gone off topic, but it's still an important part. How do you measure smoke? Smoke is an important thing to measure if you're worried about fire, okay? So we have, in Pelican Sound, we have smoke detectors. And how do they work? Well, inside each smoke detector is a radioactive element. And that radioactive element is bombarding smoke particles as they enter the smoke detector, and that causes those particles to become charged. They can be electrically charged. And there are 2 plates inside the smoke detector which pull those charges to the plates. And that flow of current turns on an alarm. Now, the problem is that radioactivity is constantly decreasing, has a half-life, as many of you have heard about radioactivity. And these detectors are no different. All the detectors use the same radioactive element. They all have the same half-life. And in about 10 years after you purchase one of these new, the radioactivity has now decreased to such a point that the smoke particles no longer get charged, and you cannot detect the smoke. Now, the alarm still sounds. That just says that the batteries are still good and that the alarm is still working. But in reality, it can't detect that there's smoke there. So I recommend to everybody, make sure you change your smoke detectors every 10 years. The other little tidbit I'll pass on is here in Pelican Sound, our smoke detectors are hardwired. That means every one of them, however many you have in your home, they're all connected together. If one goes off, they all go off. They have batteries, but the batteries are basically there in case you lose power and you have a fire at the same time. It might be kind of on the low margins or low probability, but that's a nice, safe way to go. The Some people have replaced their smoke detectors with ones from the big box stores, which are not wired together. And these are not as safe as our existing ones. I would strongly recommend to people that they try and find replacements that are the same thing. Okay, moving on. When we start working with light, the first thing we start looking at is what we call spectra. Most light contains many different colors of light. And by passing it through something like a prism, we break that light up into its colors. Each element, each atomic element has a unique signature. I've shown spectra on the right-hand side of this slide, and that is for hydrogen. So you can, if you have a spectrograph, you can see a display like this when light passes through it from hydrogen. Astronomers use this to determine what is out in space. They can sense both what we call emission spectra and absorption spectra, and they can determine what they're looking at, what type of element is producing it. Down in the lower portion of the screen, we have a neon sign, and we'll talk about that in a few seconds. So where does the light come from? The atoms absorb the energy, whatever this is causing the atoms to be excited. And the energy pushes the electrons that are in that atom into higher orbits. They don't like being up there. And as soon as they can, they release their energy and return to their original orbit. They release their energy in the form of light. So they move from one orbit to another, and they're very, very fixed. And so therefore they emit a what we call a quantum of light. And that's what we call, this is part of what we call quantum physics. So some of the atoms produce only a few colors, one or two colors, but a lot of them produce many colors. And again, we have a hydrogen emission spectrum down in the lower portion of the slide. So looking at some light sources, tungsten, an incandescent tungsten source has all colors. The filament is glowing hot and every single atom is jumping around and producing light. Neon signs, they're passing a current through a gas tube, which has a certain gas in it, maybe neon, and it produces basically one color. Many of you have noticed when you're in a parking lot at night, they are yellow parking lots. Those are sodium lights that are up there. So lasers are another type of illumination. They produce a single color, but they have a lot of special properties, which we won't bother going into. It's a little kind of deep. And what we're seeing now today, more and more and more, are light emitting diodes, LEDs. So they're becoming very common in general lighting. And your next TV may be an organic LED. You might want to think about that. So some of the properties that light has, in fact, this is not so much light as any wave phenomena. Sound waves will do the same thing. And it's what we call the Doppler effect. And the Doppler effect, the wave pitch changes if either the observer or the emitter is moving towards or away from one another. Edwin Hubble found all stars were redshifted, indicating that all stars are moving away from us. Everybody in the galaxy is moving away. So the only explanation is that the galaxy or the universe is expanding. And we don't know if it'll ever stop, but for now, it's expanding. One other thing about lights that people don't realize is the life of a light bulb. In an incandescent light bulb, the light bulb package lists the lifetimes. And most people think, well, gee, that's when it burns out. Well, no, it's not. It's when the light bulb output drops to 50%. What's happening in a tungsten light is the tungsten is being boiled off of the wire, the filament, and is coating the inside of the light bulb. Therefore, less and less light gets out through the glass envelope. And the standard is to measure and determine when that's at 50%, and that's called the life of the bulb. Most lights have a similar kind of definition. I have discovered that replacing some of the lights, such as fluorescent lights that are in closets, garages, and laundries, will produce a tremendous amount more light because the lights are coated on the inside and are no longer producing as much light. The one that surprised me was the microwave stovetop lights had been in my particular unit for many, many years and were producing very little light. I'm just replacing them with new ones, made a big gain in the light. And the other thing is with LEDs, LED lights are based on electronic components. They go through the same kind of analysis as a transistor would and don't follow the other types of light bulbs. So one of the features, or one of the pluses of using light waves is light waves can combine, which will create special conditions and information that we can use. And basically there are two kinds of combinations. There is constructive interference and there is destructive interference. Excuse me. On the left, you have constructive interference. Two light waves are combined and they produce a wave which is twice as big. In the example on the right, you have destructive interference. The two waves are the same amplitude, but they are out of phase with one another, and they literally destroy all the light. You see no light. Now, some examples of that are here in this slide. We have a gentleman who has one of these giant soap bubbles, and you can see different colors in the bubble. And those are the interference that's taking place with the two surfaces of the bubble. There's an inside and an outside surface. And they create this effect of either amplifying or destroying some of the light, leaving there just color that where the colors were amplified or diminished by the fact that they are a certain thickness of the soap film. On the right side, this is used to an advantage by opticians to make anti-reflection coatings. Many of us who have glasses will generally get these anti-reflection coatings, and they literally use the effects, the destructive effects of light to produce a way for the light to pass through the lens without losing so much in the front and rear surfaces. So another phenomenon which people who are from the north will recognize is black ice. It's a treacherous thing which most people are afraid of, with good reason. It's a thin coating of water on a surface of ice, and it makes the ice almost invisible. It really is an anti-reflection coating from good old Mother Nature. And it's, again, the same phenomena that we were just talking about. The other little point I'd like to make is that this ice often forms from what we call freezing rain. It starts off raining in the upper atmosphere, and it's warm enough so it's rain, and it starts dropping down through a cold layer. And that layer freezes or lowers the temperature of the rain dramatically, in some cases well below 0 degrees Fahrenheit, and makes the water what we call super cool. It's still water. It's not frozen, even though it's 0 degrees. And the minute it hits a surface, any surface, it freezes instantly on contact. And that's freezing rain. So going back to our destructive and or constructive and destructive interference, here's an example where these bands of light and dark appear. Here we have two optical plates, which are separated in a very small wedge with a monochromatic light coming down. And as the thickness changes by multiples of the wavelength, you get either light or dark bands. And this is an excellent way that we have as scientists to measure the flatness of these two plates. We can measure relative to one to the other exactly how flat these plates are. Each of these lines represents about 20 millionths of an inch in change in the height or the length between the two plates. Here's an example. Here's what we call an interferometer. There are 3 different interferometers I'm showing in this picture. In the lower right, in the center approximately, you can see those straight fringes, and you'll notice if you look carefully, the fringes aren't quite straight. They're a little bit bent here and there. There's a little bit of a twist to them or so on, but you can measure their departure from perfectly straight lines and actually calculate how much the plates differ and calculate their surface contours. The one on the right is a much larger distortion showing a bigger variation. Here is an interferometer that's commonly used in the field I was working in, where we were building telescope mirrors, and we had to measure the mirror to a millionth of an inch. And it's still an interferometer, works on basically the same principle. And in the images on the upper portion of this slide, the first one is a null fringe. There's no fringe whatsoever. It's just fluffed out, as we call it. And then there are straight line fringes indicating that there's a perfect match between the two, the reference and the test mirror. And then the next two, C and D, represent units that are out of focus. In the lower half, we now have what we call some common optical errors that show up, and they represent spherical aberration and coma. So when you get down to measuring things like this, it gets to be very, very important to look at all the factors that affect the measurement. Gravity is one of the biggest when you're talking about these large mirrors. On the Hubble telescope was made out of a large boule of glass that was a foot thick. And this object, or this glass, is very, very heavy, and we're trying to get it into space. So we actually bore out the back of the mirror, and we sink in holes that go all the way up to within 1 inch of the front of the mirror. in order to remove as much glass as we could. So if you look at it from the back, it's a big honeycomb of glass. Because once you get it up in space, there's no gravity. So it's very important to make sure that we support this thing when we're testing it to simulate a zero gravity. One of the things that's really challenging to do is on a ground-based telescope, where the telescope is looking at different parts of the sky and is constantly in motion, moving from maybe directly overhead down to the horizon. So gravity is changing as this mirror is changed in its orientation. And therefore, the mount has to compensate somehow to take care of this changing gravity. In addition, temperature plays an important role. Again, the Hubble mirror was made out of a material from Corning. It's a ceramic called ULE, ultra low expansion, and it had a coefficient of thermal expansion of less than 1.5 times 10 to the minus 9th. That is truly a very, very small number. And the material stability becomes an important issue. You don't want something that will have stability issues with time. And again, vibration is a problem in trying to look at these mirrors as things are shaking. It's very almost impossible to do that. So we built test stations which literally float on air. They have air mounts that support the entire chamber that it's in. And it's all done in a vacuum. So in conclusion, I hope I've shed some light on the world of measurements, made you aware that you buy water and wine by the liter, but milk by the quart. So with that, I think we're ready for some questions, maybe some answers.
Yes, and in the meantime, I'm going to go ahead and launch a poll. I'm sure that majority of you are already familiar with this feature. We just want to know how we did today. So if you don't mind answering a few questions, that would be fabulous. But yes, we are waiting for questions. Please raise your hand or type in a question in your Q&As. Mr. Vanosa, go ahead and ask your question. Go ahead and unmute yourself. Mr. Vanosa?
Can you hear me okay?
We can hear you fine.
Okay, thank you. I didn't see the mute button. Ken, way back when I was in undergraduate school in college, I remember the US was talking about going metric, and obviously they never did, but is there any more discussion about that at all? Has there ever been since the 60s and 70s?
Good question, Al. You know, what happened, there was a schedule all set up and ready to go metric, and it was back in the 60s, I believe. And Congress got cold feet. Congress was worried about the expenses that people were incurring in switching from imperial or customary measurements to metric, and they literally passed legislation which said you don't have to do it, and of course nobody did. I'll tell you one interesting little sideline. I don't know whether this is 100% true or not. It was in the last few years, they have widened Interstate 75 from 4 lanes to 6 lanes, all the way from Fort Myers through Naples. And you may notice that in the southern portion of that, when you're driving, when you're approaching an exit, there's an exit sign coming up, and it says, the exit is in 1.25 miles. And I saw that sign after they opened it up, and I said, that's a strange distance to have a sign warning you that there's the exit's coming up. And then I realized that 1.25 miles is exactly 2 kilometers. So maybe the Department of Transportation was trying to tell us something, that they were already planning for going metric, and all they had to do was just, they didn't have to put a new sign up. They just had to change the number from 1.25 miles to 2 kilometers. So I don't know whether that's true or not, but it seemed to me like it was an interesting thought. Next question.
I don't see any hands being raised. We'll give it a couple more seconds. I appreciate all of you, almost all of you. There's one more person that hasn't submitted the poll yet, but if you could, that would be great. There is Mr. McDowell. Please go ahead and mute yourself. Mr. McDowell, go ahead and speak now.
Has there ever been an estimate as to how much it would cost to change to the metric system in the United States?
Good question, Mike. I'm sure there is. I haven't seen it, quite frankly. I showed you the one slide that says that because we're not metric, it would cost us $6 billion a year. And I don't know what the overall cost was estimated. I'm sure the Congressional Budget Office put up a number someplace that Congress requested, but I haven't seen it. Next question.
There's one more hand. No, Mr. McDowell just lowered it.
Oh, now you're on again.
Mr. McDowell, you can go ahead.
I'd like to know what is the difference between the Hubble telescope and the new one that's going up. I think it's named after a former head of NASA.
Yes, thanks, Mike. The James Webb telescope
Thank you.
is scheduled to be launched October 31st of this year, down in French Guiana, near the equator, and they're going to use that to help boost the speed of the launch using the rotational speed of the Earth to get it up into space. It's approximately 10 times larger than the Hubble telescope. And it's also designed to be in more, the bandwidth is in the infrared. It's not a visible telescope like we've seen with the Hubble. It's really an infrared telescope. And it's interesting to see why they went that way. I just recently read in the New York Times about it. They're going to be able to peer close to the creation of the Big Bang. They're getting closer and closer. I think they're like 150 million light years away or something of that ilk with the Hubble. And they expect to be able to penetrate deeper and get close to the actual bang itself. But all the stars have a red shift that are moving away from us. And the stars that were created the earliest will have the biggest red shift. So they're going to be more and more into the infrared, where this telescope is designed to see. So they are trying to take advantage of what they know and what they expect the stars that are close to the edge of the universe will look like. So that's what they're planning to do. And I don't know whether, I'm sure they're going to produce some sort of images with it, and I'm sure they're going to use techniques to color the images, but it's not a visible telescope in the usual sense of the word. Anyone else have any questions?
Mr. Selger, once again, we thank you so much. And I guess next time we'll be seeing you when you'll be talking about smart home. Thank you.
Right, thank you.
Thank you.